Meet Project A.R.I.E.S, an autonomous research intelligence system that ingests live NASA data, processes it through signal analysis and ML pipelines, and generates complete academic research reports, all without a single line of manual code. The UI is minimal: a chat input, live chain of thought stream on the right. Every decision the system makes is transparent. You can watch thinking trace in real time. The architecture is a hierarchical multi-agent pipeline with 3 layers. First is ADK Brain, a 4-phase deliberative loop. The planner decomposes the user query into a multi-step plan. The reasoner thinks through each step's requirements. The router dispatches to the correct specialist agent with up to 3 retries per step. The reflector validates the output with a pass-or-fail gate before allowing the next step to proceed. This cycle continues until all steps are complete. Then the brain compiles the final output. Second is orchestrator layer. A root orchestrator parses intent via Gemini, builds a tool plan, and coordinates specialized role agents. The data collector handles API ingestion from NASA DONKI, EONET, and NOAA SWPC. The analyst handles signal processing, physics formulas, and ML inference. The validator checks anomaly detection and physical consistency. The interpreter provides scientific context and hypothesis generation. The reporter generates 8-section academic reports. The reviewer performs quality assurance on the full pipeline output. Each agent loads 19 skills at startup: code generation, causal chain building, 30+ physics formulas, ML classification and anomaly detection, data descriptors, and more, each registered as autonomous tools the agents can invoke. Tool layer connects to 4 NASA DONKI endpoints: NASA EONET for natural events, NASA APOD, and NOAA SWPC for real-time solar wind. A 30+ formula physics engine autoconverts units. The signal pipeline auto-selects different filters based on data statistics. The ML pipeline trains random forest classifiers and isolation forest anomaly detectors on demand using scikit-learn, all CPU only. A RAG-enhanced knowledge base using TF-IDF document retrieval grounds responses in retrieved context from a local corpus. Every API response is cached with a TTL, and partial failures are handled gracefully so the system continues with the remaining data. For Prompt 1, we asked to fetch recent space weather data from NASA from the last 7 days. Filter the signal data, run FFT analysis, detect any anomalies, and generate all visualizations. Then produce a complete research report. Watch the chain of thought stream on the right. The ADK brain plans 6 steps: data_collector, analyst, validator, interpreter, reporter, reviewer. The reflector validates each step with pass or fail before permitting the next. The pipeline ingests 610 data points across 3 sources: CMEs, flares, GSDs. Applies median filtering for noise reduction. Runs FFT identifying a peak frequency, total spectral power, and signal-to-noise ratio. Anomaly detection via isolation forest flags 14 outliers, which is 7% of the data. The visualizer generates 5 dashboards. The academic writer then drafts a complete 8-section research report with real computed numbers. Every number is live, no mock data, no manual intervention. Then in Prompt 2 we ask, list available physics formulas. Derive the alpha speed, compute plasma beta, and calculate the Debye length. Then, and run a counterfactual simulation. What if the CME speed was 50% higher than observed? The physics engine lists 30+ formulas and computes numerical values with automatic unit conversion from nanotesla to Tesla and cm inverse cube to meter inverse cube. It then builds a causal chain, a directed graph linking CME detections to flare activity to geomagnetic storm onsets, with UTC timestamps and confidence scores on each edge. Finally, it runs a counterfactual simulation. Given a 50% higher CME speed, it recalculates the arrival time using the transit formula, outputs the new estimated arrival date in UTC, and assigns a confidence rating to the result. This is causal AI applied to operational space weather. The agent autonomously decided which formulas to call, how to chain the events, and how to answer the what-if question without any human guidance. In third prompt, we asked to fetch recent volcanic eruption data from NASA. Plot a geospatial heat map, run ML classification and anomaly detection, estimate hazard zones, and generate a full report. Also explain the basic science of how volcanoes happen. The data collector fetches 32 real volcano events from NASA EONET. The analyst trains a random forest classifier with n estimators equals 50 and max depth equals 5 on latitude, longitude, and magnitude features, computing CV score and feature importance analysis, then runs isolation forest anomaly detection. All models train CPU only on demand with 0 GPU requirements. The visualizer generates a geospatial dashboard. The report includes ML metrics, event statistics. Template-based static fallback ensures the report is never empty even when Gemini API rate limits are hit. All 3 prompts use live NASA API data, real ML models trained on the fly, and more. The code is open source at github.com. Thank you.